Hi, and welcome to December, the December edition of According to Pete. Today we're going to continue the conversation that we started last time on transistor biasing. Last time we covered common base and we covered common collector. Today I'm going to do common emitter. It's a big one. Get a beverage of your choice and maybe some warm slippers like I got, and we'll curl around the fire and talk about transistor configurations. Let's talk about what a transistor does. So here I'm going to show you a plot. I've got, on my vertical axis, I've got IC, which is collector current, which is virtually the same as emitter current. On the bottom, I've got voltage, collector to emitter, in volts. For any given transistor, when you see this plot, what you will see is a series of curves. Yay. What we're looking at are different transistor curves for a given base current, okay? And I don't know the specific values off the top of my head for the 2N3904, which is what we're using in the example. This is sort of the beginnings of how the transistor works. We have to kind of plan what the circuit is going to do before we build it and try to understand what it's actually doing compared to what we tried to get it to design to do. You're going to have a maximum current through the part, and you're going to have a maximum voltage across the base or collector to emitter. If you've got the transistor turned on all the way, it's all the way on, the most current it can pass is going to be some value. In my case, my design example, it just happens to be 20 milliamps, okay? Now, same thing in the other direction. When you turn the transistor off all the way, so you've got that valve cranked down all the way and you're trying not to pass any current through it, it's going to have the maximum amount of voltage across it. Probably the supply voltage. If you can turn that valve off enough, you're going to get the supply voltage from collector to emitter. And in my case, conveniently enough, it happens to be 20 volts. The different values of base current cross that line at different places. The topology of the circuit is going to be, you're going to have a resistor, and a transistor, and it's an NPN, and then you got that guy, and that's going to go to ground, okay? And there's your base. And this, for a common emitter, this is where we take the output, okay? We want that point to be able to swing all the way up to the supply voltage and all the way down to zero, ideally. It is in our best interest to have that point as near to half of the supply voltage, and if this is 20 volts, half of the supply voltage is at 10 volts. That point, 10 volts, I'm going to set there. I'm going to choose this as my operating point. Again, this is where I want the voltage to sit when I got no signal in. We're setting the circuit DC, and I am trying to describe a load line. I haven't even said the word load line yet. This is a load line. What I'm showing you is that for a different base current that you pass from emitter to base, that physical point in the circuit, which is represented by this point on this line, is going to go up and down according to that load line. If I've got a low going signal, right, if I've got a sine wave coming in on the base and it's like low going, what's going to happen is it's going to turn this guy off. It's going to bring the voltage down, it's going to turn this thing off. This becomes a large resistance, and so this value goes up. Now, same thing, if I've got a high going signal there, what it's going to do, it's going to turn this thing on harder. This becomes a smaller resistance, okay? So this voltage actually comes down because that's effectively a voltage divider. So what it's going to do on the load line, when it turns on more, current goes up, this voltage goes down. So your current is rising and your voltage is decreasing. Given the load line, we're going to try to set this up so that this point right here is sitting at 10 volts DC. That would give us a nice swing all the way up to 20 and all the way down to zero, ideally. That load line also had a current associated with it, didn't it? Yes, it did. So I need 10 milliamps of collector current and 10 volts, vaguely, of VCE. Really, and that was a little fudge point, right? Because that plot that I showed you was voltage collector to emitter, not voltage collector to ground. We want to set it up for our quiescent current. We start making assumptions. And you just start with this resistor right here. You want a certain amount of voltage across this resistor because all the current, all the collector current is going to go through this guy. And so what you're going to do is you're going to say, okay, for example, I want this point sitting at 1 volt. And for 1 volt, I want to pass 10 milliamps. So that makes this resistor 100 ohms. In order to make that happen, I gotta set this divider ratio to give me, for an assumption, like we did the last time, I said 0.6 volts from emitter to base. So if that's the case, then I want to set this point at about 1.6 volts. And I need to set a resistor divider to get that value. And if I can achieve that, then I can guarantee a certain voltage across this guy, which means I can guarantee a certain amount of current through the emitter to collector. I'm setting up my bias voltage right here. Now, you want a certain amount of current going through this branch. You want enough current going through that branch to swamp out the effects of the very small base current, okay? This is gonna be microamps. So I'm gonna want the value going through here to be like an order of magnitude or 2 orders of magnitude more than that. For the sake of argument, I chose 1 milliamp because all these numbers sort of work out. And if that's the case, then you calculate it out and this gives me 18,400 ohms here and 1,600 ohms here. Now, that gives me the resistor divider that puts 1.6 volts there and allows 1 milliamp through this branch, swamping out that effect. The last thing to do is to set this point to 10 volts. How do we do that? Well, we do that by carefully choosing that value. So if I've got 10 milliamps, that goes yay, sort of like yay, then that gives me a value of 1K for this guy, okay? And this guy is called RC, right? And this one's RE, and typically this one is R1 and R2. When I first designed this circuit, I had it in my head like, I want to run this thing, man. I want to see if I can push some real current with it. So I had my quiescent current set to 50 milliamps, right? Well, I set up the circuit and everything was off, of course. Interesting thing was I had a voltmeter on this and the bias point kept changing as time went on, like a few seconds. It would get like, what's going on there? Why is this changing, man? Oh, and as I was sitting there like, something's burning. What's that? This little part, TO92 package, right? It's teeny little guy. I'm about to compare it to 2 quarter-watt resistors. This little package is only good to about 625 milliwatts, okay? And I was trying to run this thing with 10 volts and 50 milliamps through it, so I'm running half a watt, which is below its max, but it sure didn't care for it, as evidenced by the brilliant smoky aroma that was soon to emit from this thing. And really, it makes sense that it wouldn't like that much power because it's about the size of 2 little quarter-watt resistors. And quarter-watt on those resistors is max, right? So just for mass value, it's nuts if you think you're gonna pass, you know, that much power into this thing and get away with it. This is not, going back to the original example, this is not the circuit I ended up with, mostly because I'm lazy. I don't have an 18.4K. I might have a 1600 ohm lying around, but whatever. So basically, I changed this guy to be 1K, and I changed this guy to be, and you're gonna go like, what, dude, what were you thinking? It's about, what, 1147 in our, why did I do that? Well, okay, this was just the ratio. So 11, I think I calculated that out to be 1147 to give me the right ratio again. And so this ended up being a 1K resistor, and this would ended up being 3 resistors together that gave me the value of 11.47K. What I found was that I didn't have 1 volt here. I had 0.92 volt here. So there's a little less voltage here, little less collector to emitter current, or emitter to collector current. My bias voltage, or that voltage, was sitting at about 11.5 volts, right? So I've got smaller current here, which means this thing is turned off a little more, and so greater resistance, and so the voltage divider acts, greater voltage across this than that. That's why I got 11.5. Your first inclination might be to change this value and this value to adjust this and drive, more or less current through to affect that resistor. Don't do that. Don't. What you do is you just alter that value, okay? That way, so on the load line, right? This is why. If you've got this action and you start, if your bias point is sitting like a little high where you want it here, if you start changing this network, you're actually changing where your load line crosses the axis, and that's not what you set out to do. You wanted this, so keep aiming for that or you're screwed. So recalculating that value, 1150, I guess that makes sense, doesn't it? So 1150 became my new value for RC, and when I did that, I got my DC output down to 10.3 volts, okay? So it became 10.3 volts. Now, as I've got this thing configured for gain, the input signal is going to be amplified by RC over RE. This is the gain. So this value over this value, 1K over 100 ohms is a gain of 10. I've got a signal generator and I need to get signal into this thing. My signal generator has an op-amp output, and so it's a really low output impedance, right? So the source resistance that this thing has internal to it is very small. They'll dump a lot of current without too much trouble. Now, the input impedance of this guy, which is basically modeled as a single resistor, is basically R1 in parallel with R2. See, so I'm backing up to basic principles. VCC or ground, they are both signal ground, okay? So when you're putting a signal in here, it's gonna diverge in three different directions. One's gonna go that way, one's gonna go that way, one is gonna go that way, okay? So it's gonna be R1 in parallel with R2 in parallel with beta RE. The beta for this thing at a 10 milliamp current is about 200, which makes that a really big value. So what that comes out to be, as I calculated it earlier, is 843 ohms, Zin. Zin equals 843 ohms. Now that's not great, but that's what it is, so I'm gonna work with it. My generator has an output of about 1.2 volts peak to peak. And I could, since I know this is gonna be a gain of 10, I could just put this straight in there and get 12 volts peak to peak out, or that's what I expect anyway. But instead, I knew that I was gonna shoot for more gain, and we'll get there. So I knocked this down, and what I did was I basically took my output of my generator and I AC coupled it. We'll talk about that value in a sec. And then I put a 10K in line with it. So what that does is it creates a voltage divider of 10K and 843 ohms. So I get about, let's see, I measured it, it's about 92 millivolts on the base. So I knocked it down really good. And now I've got a lot of headroom for a lot of gain in there. This is just I wanted to illustrate the process by which I got the signal in and how I adjusted the level given the input impedance. Now this guy, how do we calculate the value of that guy? Just like we did once before. Start off with F equals 1 over 2 pi RC. And then you rearrange it to get C. So C equals 1 over 2 pi F R. And you just back it out for your lowest frequency of interest. Now, I had to go hunting for cap values, and I found some 470 microfarads. Like, oh, well, that's pretty good, right? That's got to be nice and low. It's less than 5 ohms at like 5 hertz. So the point of that is this guy has to be as invisible as possible over the frequency of interest, meaning every other resistance, this 10K, that 843, are much bigger, and that's where the voltage is dropping, not across that. Also, this thing can have an impact in the phase of the signal. So the bigger that value is, the less the phase is going to impact it as well. Now, getting the signal out, your output impedance of this guy is effectively RC. Z out equals RC. You're going to calculate a value of cap based on the output impedance of your amplifier and whatever impedance your load is going to be. Same thing as with the input. You want to calculate that thing so that its capacitance value is big enough that it is not impacting the equation of where the voltage is going. Let's talk about the gain now. So as I was saying before, as I've got this set up, the gain is RC over RE. In fact, it's AV, gain voltage, equals negative RC over RE. Why is it negative? Because it inverts the signal from input to output. It's 180 degrees out of phase. It is, as I've set it up, approximately 10, which is to say RC over RE. Why is that? Well, it kind of makes sense if you look at it, right? If you're turning this thing on and you've got like, well, 1 volt increase over that 100 ohm, you're going to have a 10 volt increase over that guy, okay? So you can kind of see that's how your voltages are going to fall. This guy, right, in the example I just gave, the voltage is increasing on that guy as I'm driving this up, right? So I have my high going signal here. It's turning this on more. It's creating a larger voltage across RE, okay? Now that's negative feedback, because as that voltage comes up, this voltage is holding steady because of the divider, right? So you're effectively turning this guy off. That'll take away from your gain. You're shutting off the transistor. Not only that, but you're always gonna have some of your voltage across that guy, and you're never gonna get the full swing out of your output. Now a gain of 10 is fine for certain applications, I suppose, but if you want more gain, what you can do is you can put a bypass cap across your emitter resistor. Now, what does that do? Well, a cap is AC ground, isn't it? And we're working with AC. So if our previous equation of gain is RC over RE, and now I've taken RE out of the equation, what you end up with is, and I'll write it over here, RC over little r e. RE equals resistance of the forward biased base emitter junction divided by beta. This is a much smaller value, okay? And so what happens is your gain goes way, 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 way up. You want to calculate the value of that cap against this resistor value for your low-end bandwidth, okay? You'll notice I've got a 470 here and a 470 here, because that's what I found when I went out to the bullpen hunting for parts. And then later on, I went back for one of these thinking, oh, I'll just grab another 470, and I couldn't find that bag of 470s. So this one ended up being 330, okay? It's big enough to, it's good down to like 10 hertz, 5 hertz, something like that. So it's not a big deal. Okay, so something else that happens when you add this guy, right? It seems like, geez, if I add that cap, everything's awesome. I get a whole bunch of gain. You do get a whole bunch of gain. But what also happens, remember that the input impedance of this thing is R1 in parallel with R2 in parallel with beta RE, right? Well, I just changed that value for an AC signal. In fact, I made this thing a lot lower. How much lower? Not really sure, because calculating this thing is a dicey proposition for somebody like me who's kind of lazy with math. For the first configuration, I set this up without the bypass cap. Now, what I know is that my generator, VGen, equals 1.2 volts peak to peak. And that's just so I know, okay? Now, for the purposes of calculating gain I took my scope probe and I put it directly on the base, and I put it over directly, well, not directly, but on the other side of a cap on the collector to our, our collector, right? So I'm measuring the voltages, and so AV literally equals V out over V in. So I know from the values there that it's supposed to be roughly 10, and this value got like 1150 or something. I know that one's a little higher. But when I set this circuit up and I measured V in at the base, I measured 92 V in equals 92 millivolts. So for V out, I got 952 millivolts. So that gives me a gain of about 10.3. AV equals 10.3. That's pretty close to what we expect, right? So we're cool there. Now you put the cap in. V out goes to 11.3 volts. That's quite a bit. That's a big jump. And you might go like, oh, okay, so 11.3 divided by 92 millivolts is, no. Go back and measure your V in, because I'll tell you something, that guy changed. V in is now 52 millivolts, okay? So where the input impedance was once, and if you calculate this out, it actually comes out to be 830 ohms. Without that cap, remember we calculated 843, turns out it's 830 in real practice. But when you put that cap in, suddenly you've got 52 millivolts, and that brings us down to 452 ohms input impedance, okay? But also, 11.3 volts divided by 52 milliwatts, sorry, that's a V. 11.3 divided by 52 millivolts, and that gives us a gain of AV equals 217. Holy cow! So that's a lot of gain. But as you see, your input impedance goes down. Another plus is you get that extra volt back because you're not operating in DC land for your AC signal. So you get the full swing of VCC to ground. So that's kind of cool too. So I've got my circuit set up on a breadboard. It's nothing really special. It's a whole bunch of resistors poked in holes and transistor, da-da-da-da. Here I've got my signal generator, and I've got my terminal open, and I got my waveform here. Now, one of the things, I wanted to show you like what kind of performance you can get out of this. Right now it's running 5 kilohertz. If I take it down to 50 hertz, ooh, the waveform disappears, which is kind of what we expect. But it goes down quite a bit. It was at 11 volts. Now it's at about 7 volts. So I'm nearing the low frequency cutoff for this thing. And that's going to be a direct result of that bypass cap. So the low end is less than 50 hertz, so that's not bad. Now let's crank it up. So at 100 kilohertz, I'm still at 10.8 volts. It's less than the max, but starting to taper off a bit. For the cutoff frequency, we're talking about half. You define that by half the voltage, okay? So if I'm at 11.3 peak to peak, I want to be about 5.65, and that's about the bandwidth. So it's a little more than 100 kilohertz. Let's try 200. 9.2, let's try 500 kilohertz. And now we're at about 5.2 volts, so it's a little less than 500 kilohertz is the high frequency cutoff. And you yank that cap out, so let me adjust my voltage level. I'll bring it down to 20 kilohertz. And I got my output, right, gain of 10, and my output is about 976 millivolts peak to peak, okay? So the low frequency cutoff, I'll just take it down to 20 hertz. So now I'm at 20 hertz and I'm still at 856 millivolts. So I'm still above my low frequency cutoff without that bypass cap. Let's take it straight up to 500 kilohertz. So at 500 kilohertz, I'm at 800 millivolts, 784 millivolts peak to peak. So even at 500 kilohertz, I haven't reached the high frequency cutoff of that thing. Heck, let's go for 1 megahertz. Now I'm down to 552 millivolts peak to peak. So I'm still not quite at the high frequency cutoff. This is a pretty decent little circuit for being a whole bunch of junk. stuck in a breadboard. I hate breadboards. You can poke your fingers in here and do funny things. You can mess with the waveform, right? As I was talking about before, from collector to base is effectively 180 degrees worth of phase shift. So if you couple a signal from front to back, you get negative feedback, and you might get some really wiggy stuff. Now, I don't know if you can see that waveform, and granted, this is probably, a lot of it is probably noise, right? I've got this light, this fluorescent light going right here, and I'm sure I'm picking up 60 hertz there, but tasty lead. Kids, don't try this at home. So I go front to back, and all kinds of wiggy things can happen. I can knock down the level, I can add weird artifacts, and it's probably, you know, this is like an episode of Gilligan's Island where I'm playing a radio out of my mouth. I don't know. But that's why we do electronics, right? So that's it. That is common emitter transistor configurations, quicker and dirtier for the 2N3904 and transposable to bunches of others. Remember to check us out at SparkFun_engineering on Twitter, or just at SparkFun, right, Greg? Keep your questions and your comments coming and put them down in the comment section below, or you can send them to feedback@sparkfun.com with according to Pete in the subject line. And that's it. Goodbye!